All right, and again, hello everybody, and welcome. We are continuing our discussion about a human mimicking robot. Um, Now, I called this a. I think most people, if you showed them um, this structure right here and said, "Well, what is that?" They would say, "Well, that's a piston." It's really a hydraulic cylinder. The piston is actually this right here, and this is the piston rod. I don't know that a lot of people know that. So I named the robot Pistonrobot because it runs off of hydraulic cylinders. And we had it in this pose of being in a deep knee bend where it's balanced on one foot. And I just wanted to show it moving itself from being on just one foot in a deep knee bend back up to standing on both feet with both feet on the floor. And that's just the image for you. And we're going to talk about how this can be shown to be a human mimicking robot. It really can move the way a human being moves. There's a lot to discuss. This is sort of a housekeeping video because I was talking about something in the other one in terms of the parts, and I might have said something that people would misunderstand. So I wanted to get back to that. And you can see I put in this view of it some parts just to show that the cubic inches of the part in the real robot are the same as the cubic inches in the parts split out. I split out all the parts, and I wanted to show you that. So that's what we're doing. I had mentioned this poster before. We're here still in phase 1. Now you can see the shape of the robot looks human. The proportions are about right. It's sort of modeled after my size. I just measured the length of my thigh and the length of my lower leg. We're not talking about the prime movers, which are these hydraulic cylinders. We're going to talk about them. These are kind of magic hydraulic cylinders. They would not actually function if you tried to 3D print them because they don't have the parts that are needed. But originally, a long time ago, I was saying, why don't they have a robot that mimics a human being, that really does mimic a human being? I couldn't understand why they didn't have that. And I thought, well, maybe it's not possible. So I was going to draw a robot that's a mimic of a human being, and I realized just drawing the limbs makes no sense because people would say, yeah, well, how are you going to get that to move around? And so I put these hydraulic cylinders in there to show that they are there and they're the source of the movement. A hydraulic cylinder is much closer to what a human muscle does. And I'll have a lecture on this to bring this around to where it really works. But we're talking about just the parts. And I wanted to say, if you want to print a version of this yourself, you can. And I made a FBX file that you can download that has the parts on it. And that FBX file, here's my website, and then there's a page there, discussions about a piston robot, and then you pick business versus robot science. I've added stuff to this page, but on this page is where that FBX is. And we're talking about something, particularly now that we're talking about making it real. There are pinch points where the limbs could come together and pinch you and hurt you. So any physically real object has the potential to hurt somebody. When you're managing a physically real item, my suggestion is manage it in a manner that is legally allowed and reasonable and safe. And if you cannot manage it in that way, it's my advice, don't create it as a physically real item. And this is we're in Keyshot. I took the parts of the robot and split them out into little parts. And this is the lower leg. And this was originally designed to be a military item made of metal. And so all these parts could be bolted together. And I realized if you're going to 3D print it, you could push all these parts together into one structure. And this is all one structure, this part right here. And I had mentioned to create this as a solid, and I realized that might be a little confusing. And all I really wanted to make as a solid was this opening here. I think it's hard to, first of all, this was to be a pillow block bearing in the metal version, but this will all be one piece of plastic. And I think this hole should not be here. It should just be solid plastic. And we'll go over into SketchUp and I'll show you what I'm talking about. I think it's hard to print a hole, and we should just not require the 3D printing program to do that. So let's take a look in SketchUp. And this is what I was talking about. Again, we're back to this part right here. And we can take a look at this inside of SketchUp. Okay, and we can take this and this and that and have it not be there, and that becomes a solid. And then we want it to tell us I think with the 3D drawing program that we can have it tell us where we should put the hole. And the way you can do that is, if it's a 1/4 inch hole, which is 8/30 seconds, we could make this 9/30 seconds. Oops, that's a radius. So let's be, instead of 9/30 seconds, it needs to be 9/64. So 9/64 gives a hole that is a little bigger than a 1/4 inch. And then we want another one that's 3/16. And then what we want to do is raise this out 1/16 inch. Okay, and if that was there like that, and you had this 3D printed part, you would know exactly where you're supposed to drill the hole. And you could put one here and put another one over there, and you could do that to all of these places where there's a shaft that needs to be there. And when you created the part, you could take it over to the drill press and drill this hole and then turn it over and drill that hole, and you wouldn't have to worry about the two holes matching, because they will, because the 3D printing program is going to align these holes perfectly. And so that was something I wanted to mention. And we had looked at this for printing, and SketchUp shows you that the size of this is 3.0271 cubic inches, which is what I printed on there with the texture. And I know you might be saying, man, this just looks like it wouldn't be strong enough to work. And so I wanted to evaluate that. Over here is the lower leg, and the material I was thinking to use is PETG. And this is the lower leg, and the square inches of this cross section is 0.917 square inches. And we can take a look at that material. PETG, which is what I was thinking to use, has a tensile strength of 50 MPa, megapoise atmospheres. So let's take a look at pressure. MPa right there, 2 pounds per square inch. And look at what 50 is. So that's 7,000 pounds per square inch is the tensile strength of PETG. So 0.9179 times 72, I think it was 7,200. What that says is the tensile strength of this lower leg is 6,000 pounds, which means you could pull on it with 6,000 pounds and nothing would happen. Compressive strength is usually about half of tensile strength. There's programs that give it to you absolutely, but that means you could push on this with 3,000 pounds of force and nothing would happen. And that's also usually the bending strength is about half of the tensile strength. And you might say, well, yeah, okay, but that doesn't look like that's really the place where something's going to break. Let's go over here to this foot and take a look at this part. Let's see what this is. And that comes out to be 0.1092 square inches. 0.1092 times 7,200 is 786 pounds. So you can put 786 pounds on this, and there's two of them. So that means you could push down on the foot with, 1,400 pounds of force. That's the tensile strength. The compressive strength is half of that. So you could push down on the foot with 700 pounds of force and nothing will break. And so that says to me, for a plastic robot that you're just checking out to see if this will work, that's plenty strong enough. All right, I think there's another place where people say it might fail, which is this place, these connections for the articulation of the joint. And I do like to, if possible, take a look at what's going on. And this is from Bing Desktop, Atlantic Spotted Dolphins. Here's these nice functional robots. Here are all the little problems. I see them as being little problems. I think we can solve them. Back to reality. So we can analyze this structure and see what the strength is. And I did find this article. This is from the National Institutes of Health, PLA. PLA has a tensile strength of 60 MPa. I keep saying that wrong, megapascals. I'm suggesting PETG, which is 50 pascals. Here's the structure. It's 5 millimeters wide. It had a strength of 3595 newtons. Their structure was 5 millimeters wide. My structure is 9.5 millimeters wide. So 9.5 divided by 5 is 1.9 times 3595 is 6,800 newtons. But I'm using 50 MPa instead of 60. So we need to take that. We need to take 50 divided by 60 is that times equals 5692, and there's two of these, so times 2 equals 11,000 newtons. And 11,000 newtons is 2472 pounds. So it says that this could tolerate 2472 pounds. I looked at this structure. There's the connection. I looked at this connection area in here. This is 0.1875 square inches. 0.1875 times 7,200 is 1,300 pounds. So this should have a 1,300 pound tensile strength, a 600 pound bending strength, 600 pound compressive strength, and there's two of them. So that's 1,300 pounds. That says to me that this plastic robot that we're creating just as a test is going to work fine. And here's the web page so far. I've added some stuff to it. Here's a 62 megabyte download of that image free. And she says, time's up, so I'll start another video.